All right. Hello, everyone. My name is Stephen Cox, and this is a presentation associated with my final project for my master's course in time series analysis. I'm going to be digging deep into road casualties in Great Britain, 1969 and 1984, and that's the data set I chose. This should be around a 5-minute presentation where it's mainly high level, and most of the coding and really inner details of the models can be found in the associated R markdown. So the agenda, I'm going to go over some assumptions I have about the audience so we're on the same page. Then kind of talk about a scenario I made up for this. Dive deep into the data set, just talk about it, what it is, what attributes does it have, and then dive into the model fitting. I use ASC, average squared error, as a comparison tool for the models, and then I pick the one with the lowest ASC, and I show the forecast for it out into the future. So the assumptions I have are that whoever's watching this has a basic understanding of time series analysis concepts, such as the ACF plot, the auto-correlation function, MSE, AIC and BIC, seasonality, univariate, multivariate regression, and working knowledge of neural networks, and also a basic understanding of R if you wanted to dig into the markdown associated with this. So the scenario I have is the year's 1984, and the Prime Minister has asked me to look at driver deaths, and they've collected data for the years 1969 to 1984. They want to see if I can model it successfully and then try to predict out into the next 15 months into the future. So that would be 1985 to 1999. The data set is called Seatbelt, and it's from the datasets package in R. It's shown on the right, where I called a function. I named the function, I named the data frame DF. So you have drivers killed, which is really what we're interested in. Then there's drivers, which is the number of drivers. I don't use front or rear. Those are just, was the accident in the front or the rear of the vehicle. Kilometers I use, which is the distance driven by the drivers, the petroleum price I eventually used, and then the van killed and law I do not use. But van killed is just, was there a van, and law is a 0 or 1, was a new law in place or not. So for the model fitting, right here is just a plot of the data without any transformations done to it. The top left is a realization. The top right is the ACF plot, which you can see some sinusoidal behavior there. And then the bottom right is the spectral density plot, which you can see like several peaks, where the top being at 0, but several peaks on the way down. And this is just for the driver's killed attribute. So I do a phi estimation, and then I look at the AIC and BIC for the drivers killed. So the top left is the BIC and the top right is the AIC. The top left picks an AR12 without a moving average component, and the top right has a AR12 but a moving average component of 9. So that would be an ARMA model. And then below it is the factor table associated with it. And I compare that factor table to a factor table for a seasonality factor of 4, S equals 4, just to see if there's like a seasonality component associated with this. And the way you tell is you look at the system frequencies for both tables and try to see if you can match them up, which I can here, and I also can here. This is the factor table for S equals 12. And essentially it's telling me that there could be some sort of seasonality that could be removed to help try to make this a stationary model, which will help me for modeling purposes. So this is a transformation removing that S equals 12 component. The top is the original, and the bottom is after the transformation. And this is the same S equals 12 component, but it's the plots for it. So now I can see the spectral density in the bottom right, which still has those varying peaks as we decrease, or as we go along the frequency. Sorry. And then I do the same thing for S equals 4 for a quarterly seasonal component. The top is the original, the bottom is after the transformation. And then this is also the plots where we can see the spectral density, which has actually changed some. Now there's really 3 significant peaks, and the top one is no longer at 0. So I didn't include the seasonal component S equals 4 in the forecast. because it was not accurate, but this is the S equals 12. And for all of these estimations, I removed the last 15 months of data that I had, and I reserved that aside for testing. So this is plotting out the 15 months that I do have data for, but this is those 15 replaced to see if it looks accurate, if it looks right, could it actually be reasonable? And it definitely does. It looks like it follows the pattern there. And this is just without the seasonal component. This is for an AR. This is for the ARMA model without removing any seasonality. And they look very similar. So the model fitting for VAR, this is a CCF plot, and this is when I add in the kilometers driven. And this is after the multivariate analysis for kilometers, which you can see that overlaid. The squares are what we estimated, and the circles are the original. So it overlays it really nicely for kilometers. And then driver depths is also very close, except at that end, you can see where the the original points kind of keep increasing, and our estimation decreases a little. But besides that, it matches it fairly closely. And this is a fan chart for both of them. And you can see how the pattern really continues in both, and this could be a really good model. And now for neural networks, this is the neural network model that was created when I ran it in R. I just wanted to show it here. It has those 19 inputs and 5 hidden layers. And this is a result when time is the only regressor here, and it's not very close. This is the last 15 that I removed. So this is only showing the tail end of the entire realization, and this is not very close. And this is with 100 repetitions. And then when I added additional regressors, I added petroleum price and just the number of drivers. And this gets closer. It definitely gets closer, but it's still not a very good estimator. So here's the ASE. So a REMA 1, so an AR1 with a S equals 12 and no MA portion. Then I had an ARIMA 140, an ARMA 12.5, the VAR model, and then the 2 neural network models. And that ARMA 12.5 performs the best, and that's the one I chose to forecast with here in the slides. However, if you check the R Markdown code, I have forecasts for all of the models with all the results 15 months out into the future, so out to 1999. I just didn't include it here for time's sake. So again, I chose the one with the lowest ASE, which is the ARMA model. I forecasted out 15 months into the future, and this is what it looks like. The pattern definitely seems consistent, and those are the prediction limits that are in the dashed lines. All right, I hope you enjoy the presentation.